Right now, on a mountain in Arizona, a 4-meter telescope is staring at 47 million galaxies. And what it just found is making physicists tear up their textbooks. Not amend them, tear them up. Because for 25 years, we've believed the universe ends in a slow, silent freeze. The DESI survey has just suggested we might have called the ending completely wrong. And there are 10 specific findings, 10, that don't just bend cosmology, they might be breaking it. Stick around, because what's coming up at number 8 changed everything I thought I knew about how this whole show ends. G'day, you're with Curious Physics AU, and today we're walking through the 10 DESI discoveries forcing scientists to rewrite the fate of the cosmos. Let's get into it. Number 1, the biggest map ever made. Forget the maps in your old high school atlas. DESI, the dark energy spectroscopic instrument, has built the largest three-dimensional map of the universe in human history. We're talking 47 million galaxies and quasars charted across 11 billion years of cosmic time. To put that in perspective, if every galaxy on that map were a single grain of sand, you'd have enough sand to bury the MCG knee-deep. And here's the kicker. DESI didn't just take pretty pictures. It measured the precise distances and velocities of these galaxies using something called baryon acoustic oscillations. Basically, frozen sound waves left over from the Big Bang itself. Think of them as the universe's tape measure. And when you've got the universe's tape measure, you can finally start answering the question we've been asking since Edwin Hubble in 1929. What's actually pulling this thing apart? Number 2, the model of cosmology that's been our Bible for 25 years just cracked. It's called lambda CDM. The lambda is a Greek letter Einstein himself stuck into his equations to represent a cosmological constant, a steady, unchanging push that fills every cubic metre of space and drives galaxies apart at a constant rate. For a quarter of a century, this model has predicted everything from the cosmic microwave background to galaxy formation with eerie accuracy. It's been called the standard model of cosmology, until DESI looked harder. The DESI data, when combined with the cosmic microwave background and type 1a supernovae, disagrees with lambda CDM at up to 4.2 sigma. In physics, sigma is basically how loudly the data is screaming at you. 3 sigma is interesting. 4 sigma is this might be real. 5 sigma is pop the champagne, write the textbook. We are knocking on that door. Number 3, dark energy isn't a constant. It's changing. This is the headline finding, and it's a beauty. Dark energy makes up roughly 68% of everything in the universe. We've never seen it directly, never bottled it, never measured it in a lab. But we know it's there because the galaxies are flying apart faster every year. The whole point of lambda CDM was that this energy was constant. Same density a billion years ago, same density a billion years from now. DESI's data says, nope. The data points show dark energy was stronger in the past, and it's weaker now. It's evolving. It's dynamic. And if you've ever heard a physicist mutter W0 WA under their breath, that's the parameter they're testing. And the DESI numbers are pointing away from a constant universe and toward one where the rules are quietly shifting beneath our feet. Number 4, the signal is getting stronger, not weaker. When DESI's first results dropped in 2024, the evidence for evolving dark energy was around 2.6 sigma. Suspicious, but not solid. The natural reaction in good science is, cool story, let's see if it survives more data. Most weird signals don't. They wash out. They turn out to be calibration glitches or unlucky statistics. But when DESI's data release 2 dropped in March 2025, the signal didn't shrink. It grew to 3.1 sigma with cosmic microwave background data alone, up to 4.2 sigma when supernova data was added. And this is from researchers across more than 70 institutions worldwide, including teams here in Australia at the Australian National University in Canberra and at Mount Stromlo Observatory. The signal is hardening. The universe isn't being shy. It's telling us something. And we're finally fluent enough to listen. Number 5. In the past, dark energy was a phantom. Sounds like a Marvel villain. Actually, a real physics term. The strength of dark energy is described by something called the equation of state, written as W. If W equals -1 exactly, dark energy is a perfect cosmological constant. If W drops below -1, say -1.2, dark energy is in phantom territory. And phantom dark energy is the stuff of physics nightmares. It doesn't just push galaxies apart, it accelerates so fast it can rip atoms in half. Space-time itself starts to tear at the seams. The DESI data suggests dark energy used to be in this phantom state in the early universe, billions of years ago, which means at one point the cosmos was being shoved apart even harder than we already thought. And that's the easy part of the story. Now, if you're still with me, the next 5 are where it gets properly mind-bending. Hit subscribe right now if you haven't, because what's coming up at number 8 is the discovery that's making astrophysicists question whether we know our cosmos at all. Number 6. Today, dark energy is weakening. This is where it flips. In the early universe, phantom. Strong, ripping, accelerating everything outward. But as DESI tracks dark energy across the last 11 billion years, the data shows the strength dropping. Right now, in 2026, dark energy appears to be in the regime where W is greater than -1. In plain English, the cosmic accelerator pedal is being eased off. The universe is still expanding, galaxies are still receding, but the rate at which expansion accelerates is slowing. Imagine you're driving from Sydney to Melbourne, flat out at 200 kilometres an hour, and somewhere near Albury, you start gently lifting your foot. You're still moving forward, you're still cracking on, but the engine isn't roaring like it used to. That, give or take, is what dark energy seems to be doing right now. Number 7. The big freeze might be off the table. For decades, the predicted ending of the universe has been the big freeze, also called heat death. Galaxies drift apart forever, stars burn through their fuel and go dark, black holes evaporate over trillions of years, and eventually the cosmos becomes a cold, empty, lightless soup at near absolute zero. It's a depressing ending, but at least it's tidy. The big freeze depends on dark energy staying constant or growing. If dark energy is weakening, as DESI suggests, then a true big freeze becomes uncertain. Maybe expansion enters a coasting phase, where it just keeps cruising at a steady speed forever. Maybe it stops altogether. Or maybe, and this is where it gets spicy, maybe expansion reverses and the universe starts pulling itself back together. Which leads us straight to number 8. Number 8. The Big Crunch is back from the dead. The Big Crunch was an idea cosmologists loved in the 1990s. The picture was simple. Gravity wins. Eventually, the expansion of the universe slows, stops, reverses, and everything collapses back into a single, hot, dense point. A Big Bang in reverse. Then, in 1998, 2 teams discovered the universe wasn't slowing down, it was accelerating. Dark energy entered the chat, the Big Crunch was binned, and we settled in for an icy ending. Now, with DESI's data showing dark energy weakening, the Big Crunch has crawled out of the grave. A 2026 paper from physicists at Cornell, building on DESI and dark energy survey data from Chile, suggested that the cosmological constant might actually be slightly negative. And if that's true, every galaxy, every star, every atom on Earth every grain of sand at Bondi, every snowflake on Mount Kosciuszko, eventually gets pulled back together. Not torn apart, collapsed in. Number 9. The Hubble tension might finally make sense. There's been a problem in cosmology for years called the Hubble tension. When you measure how fast the universe is expanding using nearby supernovae, you get one number. When you measure it using the cosmic microwave background, the leftover radiation from the Big Bang, you get a different number. They don't match. They should. The mismatch has been driving cosmologists round the bend for nearly a decade. Because if both methods are correct, something is wrong with our model of the universe. Evolving dark energy might be the missing piece. If dark energy was stronger in the past and weaker now, the expansion rate measured at different cosmic epochs would naturally come out different, without needing exotic new particles or hidden physics. The DESI results don't fully solve the Hubble tension yet, but for the first time, they offer a believable, data-driven explanation for why our two best measurements have refused to agree. Number 10. The fate of the universe might be matter-dominated. This is the deepest, weirdest implication of all. For 25 years, we've assumed dark energy wins. It's 68% of the cosmos. It runs the show. But a peer-reviewed analysis published in late 2025, running independent fits on DESI, CMB, and supernova data separately, found that when you stop assuming dark energy is constant, the long-term fate of the universe doesn't end up dark energy dominated at all. It ends up matter dominated, meaning the regular stuff, galaxies, gas, dust, dark matter, even the iron in your blood and the wool in your jumper, eventually pulls the cosmos back to itself. The thing we thought was a sideshow turns out to be the main event. The universe doesn't fade, it doesn't tear, it comes home. And that, mate, is why the DESI survey just forced cosmology into one of the biggest rewrites in 100 years. Bigger than dark matter, bigger than the Higgs, maybe bigger than the Big Bang itself. Now, I want to be honest with you. This is still being debated. A November 2025 paper argued that DESI's evidence isn't quite as airtight as it sounds, that there are tensions between the datasets, and we need to be cautious. The full DESI 5-year results are due in 2027. Until then, we're in one of those rare, delicious moments in physics where the textbooks aren't settled, where curiosity beats certainty. And honestly, that's the best place to be. If this video sparked something for you, smash that like button, subscribe to Curious Physics AU, and drop a comment. Do you reckon the universe ends in a freeze, a rip, or a crunch? Next video, we're falling into a black hole. Hope you don't survive. See you there.